Okay. So starting from the top. My name is Qing, and I'm here to present Neon. And Neon is work done with my collaborators from UCSD. And Neon is a system designed to provide system support for derived data management. So modern organizations and government agencies now are storing more and more data, and they would probably want to enforce a range of different information management policies on the data that they have. So, for example, if you're a company and you have, insensitive employee data, you might want to be able to say who may access data, how it can be accessed, and what it can be used for. And they have these different policies in order to be able to comply with these regulatory constraints set by the government, such as the HIPAA, which is the Healthcare Information Privacy Protection Act, or the FISMA, etc. They want to be able to provide to protect their trade secrets from being leaked outside of their organization, or prevent identity theft. We've all known that somebody who's gotten their ID stolen online is because of some company who didn't have enough stringent policies to prevent identity or the theft of their credit card files, etc., and also to avoid brand damage. So even though there's a bunch of policies that these companies and organizations want to enforce on data, such as custom records should be encrypted, GPL files should not be used to build product binaries if you're Microsoft, etc. The enforcement mechanisms are actually about the data containers. So the canonical example is a file. Well, the two I'm going to give here is an encrypted file system or a file-based authentication. So you have some sensitive data, and once you store it into the file system, the data is protected. But once you remove the data outside its container, then it loses that mechanism to be able to enforce the policies on the data. And similar with a file, right? You have read and write access on the file, but as soon as you copy and paste the data outside of the file, then you lose those protection mechanisms. So what we strive to do with Neon is to be able to shorten the gap between enforcing mechanisms on the containers of the files versus the data itself. So what Neon does is it's a derived data management system within a protected network. And what Neon does is that it tags data with its own policy. And we're able to track derived data flows, such as copy and paste, if you copy and paste some data outside of the file, and we're not keeping track of containers. And the mechanism that we use here is taint tracking. So just to note that taint tracking is not it was not invented by us. It has been around for a while. But taint tracking has mostly been used for malware prevention and detection, whereas we want to sort of extend this into support of a wider variety of applications, which I'll give you some examples in the upcoming slides. And we want our system to be able to provide, to support multiple simultaneous policies. And how we do this is we use multiple taints in our system. We call them tints. And we want to be able to enforce the policies across the network. And one of our high-level goals of our system is to be able to operate transparently. And what I mean by that is to support unmodified operating systems and applications, and to not require any hardware support. And just to note, our system is not targeted towards we are targeted towards accidental violations, and we're not trying to address adversarial models such as covert channels, etc. So with that in mind, I'm going to give some applications that we're targeting with the system. So what we want to do is we want to track derived data and not the containers of data. So you're a company, as I mentioned earlier. You have all the companies have some file that has their employee salaries. And somebody from HR copies and pastes this sensitive data into an email. Maybe they meant to send it within the network, but for some reason, maybe the autocomplete completed the wrong address. They accidentally sent it outside the network. So what we want to be able to do is to actually track the data that was pasted into the email and say this is also sensitive, and be able to have some sort of exfiltration policy at the edge of the network to prevent this from happening. Another thing that we want to do is be able to track provenance of data. So the example I'm going to give here is compile. And here is just tracking the provenance of source code. So the question at hand is, does my application contain any GPL source? If you're Microsoft or, not to put Microsoft on the stand here, but so what you want to do is maybe you want to use different tints for the different kinds of source files that you have. Let's say here you have your own homemade code in red, and then you maybe have GPL code in yellow, tinted in yellow. And what you can do is you can compile your source files using your favorite compiler. And what you would like to do is have the tint propagate to the object file. So you can see here from the example that the orange file is indeed derived from file C, in which case then you should be careful not want to ship that to your customers. And the other example I'm going to give is we want to be able to provide a fine-grained solution, and there are some advantages of doing this way, which is it guards against false tinting. So here's an example of archiving. So I have some tinted files in a directory that you then archive using tar. The resulting tar file that you have will now be a mixture of all the tints that you had in your original directory. So now you want to untar this somewhere. What you'd like to be able to do is to recover all of the tints in your file. So if you did tracking at a very coarse grain level, what happens is then when you untar the files, then they're all going to turn out to be purple. So hopefully the color is clear on the projector. So with some of the applications we're targeting, I would like to go into some of the design challenges into building Neon. So here are the design challenges, which are transparency, fine-grained data tracking, to be able to try to provide low overhead and provide a network-wide solution, as well as keep it persistent. So I'll go into each one of these in detail. So what we mean by transparency is we don't want to modify any operating systems or applications. And there has been systems out there that provides distributed information flow control, such as Asbestos or HiStar and some of these other ones, but they require you to modify the operating system, and some require you to modify the applications, and some provide you need special hardware to provide this distributed information flow control. And so what our approach is that we're going to implement this in the virtual machine layer, and in particular we're using Zen. And what we do is we want to emulate instructions that propagate tint in QEMU. And our system is built upon a system by Ho in 2006, and their system was designed mainly for malware detection and prevention. So here's the basic Neon architecture. Our trusted computing base is pretty much Zen, and as well as QEMU running on domain 0, and whoever wants to use our service can import any guest operating system they would like, and once they do it, we provide full system data tracking for them. So the second goal we want to do is to be able to provide very fine-grained data tracking. And how we do this is we tint at the byte granularity. So we tag tinted bytes with a 32-bit tag, and each bit in the tag can represent a different policy that you want to enforce on that data that you tagged. So what we do is then we unmap pages containing tinted data, and so that anytime that page is touched in the future, then we trap into emulation mode when we're handling tinted data, and then we propagate it via QEMU. So here's a pictorial example. So I have some instructions that are running on the virtual CPU on a guest, and everything is fine. And all of a sudden, you're accessing a tinted page. Now we trap and give control over to QEMU, where the instructions are emulated and tint is propagated. So just a further example. So you have an add instruction with two sources that are of different tints. You have a red tint and a yellow tint. As a result, we mark the destination register as a mixture of those. So we want to reduce the overhead in our system. And how we do this is we do it both in memory and CPU overhead. So in terms of memory, we represent the tint information in a two-level table. And this table is just very similar to a page table, essentially. And we recover memory over time. We coalesce contiguous tints to take advantage of locality. On the CPU side, we want to only emulate when we're propagating tint. So when you're not touching tinted data, we want you to be able to execute at vanilla speeds, vanilla kernel speeds. So, our goal is to be able to, we want the amount of emulation time to be proportional to the amount of time of tints executing the system. And so we enter emulation mode, as I mentioned earlier, when we're touching a tinted page, and we switch back into direct execution after 50 instructions of not touching any tinted data. So another one of our goals is to make this a network-wide solution, and we want to enforce various policies. Like, say if you're a company, you probably want this to work throughout your company. And how we do this is we want to propagate tints across the network. And so what we did for our system is we represent tint in bytes, or tint of bytes in packets. So what we did here is we overloaded the TLS field in the IP header with tint metadata. And this was a design decision mostly made for the expediency of prototyping. We realized that there's some drawbacks for doing this way. For example, now we're limited to 8 bits of tint metadata versus 32-bit on a single host, and you lose some granularity from the packet granularity versus byte granularity when you have to write to the network. And similarly, we also tried to make this a persistent solution. So we wanted to keep tint persistent on disk. And how we implemented in our system in Neon is we overloaded the group ID field to store tint metadata. And again, this is a decision made for the expediency of prototyping. Again, we lose some granularity when you have to write out to disk. And what we did here for implementation is we modify the NFS server to be tint-aware, and that whenever we're updating, whenever we're writing a tinted file to the file server, we update the GID accordingly, depending on what data is tinted in the file. And furthermore, when we're reading a file, we update the TLS header in the packet when we're sending out. So just here's a concrete example. You have a guest OS that's requesting some tinted data over the network. The tinted data comes through QEMU, where the packet data then that's tinted gets marked, and the tint table is updated. Then you can now pass the data to the guest. Similarly, when you're writing some tinted data to the file server, because you're operating on the tinted data, it gets trapped to QEMU. And then you look to see, you index into the tint table, and then you mark the headers and also the GID such that it's propagated back to the file server. So now giving you the architecture of our system, I want to do some evaluations. So first, I'd like to say that we implemented Neon, and it's a working system, and we used it to demonstrate a wide range of applications. So all the applications I mentioned in the beginning of the talk, such as if you copy and pasted some data from one Emacs buffer out to another, that is indeed tagged, and you can enforce policies on that, or the compile. So the tracking the provenance of code, or archiving, and another one we did that I didn't mention was encryption. So we said anything that has this tint, when it's written out to disk, has to be encrypted, etc. All of these things are implemented, we tried with our system. And if you're curious, you can check out our V paper to read about the details. So now we want to look at Neon's overhead in terms of CPU overhead and space overhead for having such a fine-grained data tracking system. So how expensive is this? What we did is that we did a local copy of a 4 megabyte tinted file using just regular copy. And what we did is we had an in-memory file system, so no disk or network in here. And one file had 2 tints, and the other one had 8 tints. So in our evaluation, we see that for this particular metric, we had a magnitude higher CPU overhead and 20 to 40% memory overhead for keeping track of the tints. So you can see there is a bit of overhead of using our system. And we say this is future work to try and optimize to make this more practical. Another test that we did is a remote copy. This is almost the same same thing, except for now we're copying over the network and copying to this file server. So in this example, you only see a 2 times CPU overhead versus 10 times, and the difference is there's more I/O happening. So the I/O overhead reduces the tint overhead, the impact of the tint overhead. So if you have a lot of I/O in your system, it could potentially be a usable system. So another metric that I want to show you is we want to look at the space overhead of compiling untinted source code, tinted, untinted, and then tinted again. So the blue region is tinted and the white region is untinted. So, and the blue line is the tint table overhead, and the red line is the amount of tinted bytes, and the x-axis is time, and the y-axis is memory overhead. So the important thing to note on this graph is just that even though we're executing untinted data, when we're executing untinted data, the amount of tint drastically reduces in our system, so that it is somewhat proportional to the amount of active tints in the system, and not forever growing. So with that, I'd like to summarize. So we've implemented Neon, and Neon is a transparent network-wide data management system. Is capable of supporting simultaneous policies via tints, and it's capable of doing derived data tracking, such as copy and paste and compilation. And it supports a wide range of different policies. In ours, we've done containment, tracking provenance, and encryption. And I can imagine there's a lot more applications you can do with the system. So our prototype demonstrated that it's feasible. Not to say that it doesn't have a high overhead, but we still find that it is feasible when we're compared to government systems where they have to disconnect everything in order to enforce their policies on the data that they have. So to conclude, we think this is a very cool system, and we think that with great power comes high emulation cost. With that, I conclude my talk. Any questions? Currently, it's not, but we can probably patch it up and put it on a website somewhere so it is for you. It's in a Mercurial repository somewhere. But I guess because we modify the NFS server and everything, so I guess you would need some configuration to get it up and running. But
so once you stored your tints, say on a modified NFS, basically the only way you can read the data is using your system. Is that correct?
Can you?
How do you store the tints on your modified NFS server?
So we're using we overloaded the GID field on the files.
Oh, I see. Okay.
Yeah. So that's a bit of a hack. The network end. That's
fun. Have you looked at binary translation to try and reduce the overhead of your emulated reads and writes?
There's lots of different proposals for how to make the system faster, and you mentioned one where if QEMU can be improved to using emulation binary writing, as well as I think there are some proposed hardware changes that adds tagging of memory in the hardware. All of these solutions can potentially make our system a lot faster. I think our bottleneck is essentially when we have to trap into emulation mode, the switching and the emulating instructions is what keeps us slow.
I have a second question. Have you had problems with the tints kind of escaping and the whole sort of memory?
The tint explosion problem.
Yeah.
So in our test, we haven't exhibited anything like that, and we've actually tried very hard to try and get tint to kind of spew everywhere. And what we've done is we've tinted executables and tried to execute them in hopes that they will actually spew tint everywhere, and that didn't happen. It would only happen if there are some symbols in the executable that you're touching, and the data that you're outputting is a result of doing some operations with the symbols themselves. Otherwise, it didn't. And I think there's another paper that also did instruction level memory tinting, and they also, not tinting, memory tinting, and they also mentioned that they didn't really see any as well. But another thing that we did to prevent this from happening is, like, I think we don't tint any control registers, so that, you know, this is not control flow.
Right, because I've done a sort of moderate amount of work with Valgrind, the dynamically translating thing, looking at something similar to tint tracking. We found that GCC kept generating code that, you know, would turn a perfectly ordinary-looking pointer expression into something involving a stack pointer, and then suddenly the stack pointer.
Yeah, we don't
tied
tint.
into that.
Yeah, we don't tint the stack pointer, and just yeah.
Okay.
So.
Any others?
I would imagine that there's a whole class of data transformations where basically the program counter is the thing that gets affected by the tint. Do you tint the program counter, and then
No,
if you do, how do you untint
we don't
it?
tint. We don't tint the program counter.
So if I gzip a file, then I'm probably not. The tint probably won't propagate through it, right?
Yes and no. We've actually tried gzip, and there are some. They index a table, right? So they index a table to generate the output, but the indexes memory that can be potentially tinted using it. And I think in our system we actually did tint. Like if you were doing indirect
It got through
tinting,
somehow.
yeah. So I think it worked in our system, but there could be scenarios where it doesn't work. So yeah.
Thank you.